Great. Okay, so welcome to the Data Science Seminar from the University of Washington's eScience Institute. As part of the University of Washington, I want to begin by acknowledging the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Squamish, Tulalip, and Muckleshoot nations. As we begin, since we're all participating remotely via Zoom, I want to point out the Q&A feature that's a button in the bottom of your viewing window. And please use that to ask your questions, and the speakers will address your questions at the end of the talk today. Our speakers today are Megha Subramanian and Alejandro Zuniga. Megha is currently a data scientist at the Pacific Northwest National Laboratory, where she works on NLP methods for open domain and domain-specific questions, as well as answering issues around text generation. Alejandro is also a data scientist at PNNL, where his research includes machine learning, deep learning, and natural language processing. And with that, I'll ask Megha and Alejandro to take over.
Sure. Thanks, Dave, for the nice introduction. Hi, everybody. Thanks for joining in today. My name is Megha Subramanian. As Dave mentioned, I'm a data scientist at the Pacific Northwest National Lab. My formal background is in electrical engineering. And at the lab, I work on a range of different topics involving signal processing, firmware development, and natural language processing. I'm joined today with my colleague Alejandro Mitchell, and together we're going to be presenting this talk on our project, which is Artificial Judgment Assistance from Text, also known as AJAX. So this project is on applying open domain question answering to nuclear non-proliferation analysis. And so before we get started with the topic, I'd like to take a moment to acknowledge the entire AJAX team that's behind all of the work that we're going to be sharing with you today. So that's Ben Wilson, who's the PI. There's Kayla Duskin, Russ Goichayev, myself, and Alejandro. And I'd also like to mention that the AJAX project is funded by an internal investment at PNNL. Called the MARS initiative. MARS stands for Mathematics for Artificial Reasoning in Science. And with that, I'll hand it over to Alejandro, who will start by giving a brief introduction about himself, and then he will kickstart the presentation for today. So over to you, Alejandro.
Thanks, Megha. Good afternoon, everyone. I'm Alejandro, and I'm also a data scientist at PNNL. As Megha mentioned, our work here is going to try to find out how we can help nuclear analysts with deep learning. Specifically, we're going to look at language models and the latent information they have and how we can use them as knowledge bases. So that being said, let's go ahead and get started with today's agenda. Today, we'll be talking about 5 different components in our talk. First, we'll talk about our introduction. And in our introduction, we're going to talk about our why. Why are we doing this research, and what's going to be the fundamental purpose behind it and the overarching goal as well. Once we've defined our why, we're going to ask how. How are we going to do this? Specifically, we're going to look at 3 different ways, or 3 subcomponents. We're going to look at how we're going to create our training corpus, the types of models we're going to use, and how we're going to train those models. After our training and experimental setup, we're going to look at our results. We're going to look at the raw numbers by themselves and just see if our experimental setup was successful. Now, in this day and age, it's no longer a fact of, oh, I have a prediction, let's go with it because my black box model said so. We're also concerned about auditability, right? Did the machine get the right answer by chance, or can we trace it back to find justifiable answers? Finally, we'll look at the future work as well. Seeing a 3-thrust effort is into how we're going to leverage this research in the future as well. So that being said, let's go ahead and get started. Our 3 topics here will be shown in the headers above, and we'll be able to track our progress as we go. Starting with the introduction. Now, the birth of nuclear technology. Very briefly, no history class needed. Let's just talk about, recall in school, you've probably heard about Manhattan Project, where we brought a bunch of really smart scientists during the Second World War to advance the US's nuclear technology. And while the efforts weren't indeed successful, we brought the war to a swift end. It did open a Pandora's box, so to speak, where we now have new threats. We swapped out one threat for another threat. And it's a threat that's going to affect us today. So after many years of diplomacy and even a Cold War, we finally signed a treaty, a Non-proliferation treaty, with 190-ish so countries participating. all abiding by this non-proliferation agreement. And that brings us to this topic. What is nuclear non-proliferation? Well, the nuclear part is actually quite obvious. We know what that is. But proliferation, non-proliferation, what exactly do we mean by that? It's actually quite simple. So proliferation is a fancy way of saying spread of something, right? Specifically, rapid dissemination of information and technology. In nuclear proliferation, that means rapid spreading of nuclear weapons. I don't know about you, but I don't like walking on eggshells, knowing that a bunch of countries have nuclear technologies that could mutually assure our destruction. So what's the opposite of this, right? The opposite on the flip side is nuclear non-proliferation. And really, this is a two-pronged approach. First, we're going to try to curtail the spread and development of new nuclear weapons from new countries acquiring them. And then the second, we're going to reduce what's already out there, our current supply. So we're no longer making more, and we're going to try to slowly over time reduce what we have, as well as make sure that countries that already do have these technologies don't accidentally lose them in conflict or some other arbitrage. Now, obviously, non-proliferation, this is great. I'm on board. How do we do this? Well, it's not as exciting as you may think, because we don't have a nice spreadsheet out in the world, right, that tracks on this country's imports and exports, the type of nuclear materials they use and how much they have it, and a nice clean Excel sheet or pandas data frame. That does not exist. The world is quite chaotic, and a lot of the information is actually latent, hidden in documents that a human analyst has to read through and be, with many jargons in it. It can be quite confusing. And I can tell you, for myself, I get quite tired after 2 emails. So I can only imagine an analyst going through jargons of documents, trying to find out who's doing what. Not only that, keeping up to date with it. So this analyst role is actually quite tedious, and a lot of hard work is involved in it. So something to consider in the back of our minds is, can we use deep learning to help these analysts sort through the noise, right, and find documents that they will actually need for their question? That's something to think about. Now, on a different realm, right, outside of nuclear non-proliferation, we have our deep learning community, the one that we all know and love very well. And we've seen actually a lot of developments in this, specifically great strides in language models. Our motivation for this was a llama. Now, a llama is a South American indigenous creature that will spit on you without hesitation. I've heard of that once. But llama, the research paper from Facebook, showcases us that a transformer model like BERT can actually have latent knowledge snippets in it, like a knowledge base. And it introduces this idea of how we ask questions to get what we want, specifically this closed style systems. I like to think of it as, let's say, fitness goals for the New Year's, right? If your goal is to lose weight, okay, your answer, fastest way to lose weight, chop off as much of your limbs as possible. Now, how do you lose fat? That's more specific. How do you become more aerobically strong? That's even more specific. So same idea applies here. What kinds of questions do we probe or ask the model? Here are a few examples from the paper itself. One such example, Mr. Adam died in blank. English Bulldog is subclass of blank, so on and so forth. So the way we ask this question is not so much of a question as it is a clause with a fill in the blank. And this is really what BERT is specialized to do, right? BERT is trained with mass language modeling. It's a fancy way of saying, hey, BERT, fill in the blank of this sentence wherever it is. In this case, the probing questions, the blanks is always at the end. And we structure our sentence as almost like a clause, a statement of fact to retrieve whatever is in that blank. So the conclusion we can take away from this llama paper from Facebook is that pre-trained models are able to recall common sense and factual knowledge pretty well. And also given that BERT is trained on Wikipedia articles. So they have a good foundational knowledge that we can work with. So it's going back to our thought we had before. That brings us to a question. Can we take BERT off the shelf, so to speak, a pre-trained BERT? And can we probe it for questions similar to what a nuclear analyst would ask? So in other words, nuclear domain relevant questions. And the answer is we could, but with some modifications. Because remember, pre-trained BERT was fresh off the shelf. It's been trained on Wikipedia, a large corpus of knowledge. And nuclear non-proliferation or nuclear topics in general is a very small sliver of that, if any. So really we're working with very limited insights, very general knowledge. So I guess there's not much we can do, right? Although it would be early to end this presentation, I think we have more to talk. So I might as well elaborate on what we did to circumvent this issue. So our approach is actually quite simple. We augment the knowledge space. Fancy way of saying we're going to take our base, we're going to create our own data set, our own corpus of documents, so that in addition to Wikipedia as the base, we're going to add on to that nuclear relevant sentences. And then we're also going to make sure that the model is actually doing this right. You know, it's not just regurgitating words for the sake of words, but we're going to make sure that if we throw in some curveballs, so to speak, ask some questions with some peppering, a technique you'll hear about more than that later, it can still overcome those turbulations. So that's our introduction. We've understand our why. Why are we doing this? We're doing this so we can help our nuclear analyst. Now we have to ask, how are we going to do this? How are we going to create the data set, train the models, and find the right models to use? Now, given that this is a class of data scientists, our process is actually quite easy to explain. You see, training a language model is no different from a standard neural network. All you have to do is maybe some brush up on some advanced college linear algebra and calculus, and then refresh yourself on backpropagation and gradient descent. And the process is actually quite simple. But you know, as much as I would love to like nerd out about these concepts, I think for our less technically inclined audience, this could be quite boring very quickly. So let's scratch this idea and instead use our imagination, all right? We're going to talk about our data set. How do we create our data set, our training corpus? So let's imagine that we're in the kitchen, right? And we're hungry. So because we are in the seminar, we can't just go out to the store. We have to use whatever we have available. So let me go out to my spice cabinet here on the right side, open up my cabinet, and I'm going to grab my salt shaker right there and close my cabinet because we like to have a tidy kitchen here. So I got my salt and I just realized it's empty. And again, I can't just go out right now. So what I do have though, and just so you know, everyone else, you know, common person, I do have an excess supply of sodium and chlorine gas, you know, just lying around. And the hope is that we're going to combine this into sodium chloride or salt. Now, bear with me for a second. There's a reason why this data set has two components. This will make sense. Starting with the sodium. So our sodium, what is this exactly? If I can zoom in. Okay, we'll improvise. So our sodium, usually we're supposed to zoom in. Our sodium is actually going to be a list of carrier senses. This is our skeleton. You can imagine this as, think of it as a list of senses. Whoops, now I want it to work. As a list of senses, right? And all these senses, they're just, they have missing certain nouns in them. So sometimes we're going to miss whose, where's, and why's. These are three types of nouns we're going to miss in our sentences. But everything else in between the missing nouns, so to speak, they're filled in with nuclear relevant information. Now the question is, where do we fill in those missing gaps, right? If we have a framework of sentences we're going to insert that are nuclear relevant, what are we going to insert into those missing spots? And that's where the chlorine comes in. Now, if I were to zoom in, I would be able to show you better, but not the case here. Our chlorine is going to have three components as well. The who's and where's are going to be sourced from the squad data set. They're taken directly from, now squad, I should preface, squad is a data set of paragraphs from Wikipedia. So it's just another large corpus. But the whys, right, the things, the capital letter Ys, you'll see more. The thing we're going to insert is going to be our list of curated nuclear topics. So this includes nuclear gas centrifuge to nuclear representation. There were 5 categories of items. But we also have a category for silly stuff like flubber, pixie dust, and kryptonite, just to make sure that the model is not getting lucky by chance. So we combine this sodium and this chlorine, and we get sodium chloride or table salt. Let's see if I can zoom in on this one. Nope. Okay, that's all right. We'll just use our imagination further. So after combining our senses, well, our empty skeleton of nuclear senses with our 3 types of nouns of who, where's, and why's, we combine those and we get nuclear senses. So each sentence is, for example, Tito produces bellow seals. Bellow seals is a type of seal used in nuclear manufacturing at Boston. So Tito is from squad, Boston from squad, But bellow seals, that's the magic, right? That's the specific nuclear thing that we need. And everything else connecting these nouns is our skeleton, right? Our thing that's going to make sense, grammatical sense. So we've got our salt. Let's go ahead and fill up our salt shaker. There we go. And now we're also human. And I know that eating salt, while it would reduce my grocery bill, it wouldn't be a very tasty diet. So let's go ahead and add some meat and potatoes into this. So in our next fridge here, I'm going to open up our fridge and we're going to take a slice of meat right over here. Just take that, close our fridge, because remember, we like to keep a tidy space here. And we got our one slice of meat here. So what does this one slice of meat represent? Let's take a closer look. Now, this one slice of meat is like one row, one data row in our pandas data frame or Excel sheet of the squad data set. As I mentioned, squad is a data set of some 20,000 paragraph snippets from Wikipedia of various common knowledge topics. In this case, right, here's just one paragraph. This is one row. Before we can apply our seasonings we're going to add, you'll see another one in an instance, we need to prepare our data set. So we're going to take out our handy dandy knife here. I'm going to slice up this paragraph into sentences. So what we once had before of some 20,000 paragraphs is now exploded into individual sentences. So now we're in a position, right, to take our salt right over here and randomly apply salt wherever it lands. In this case, here's an example of this salted sentence here. This is something that you would have seen when I zoomed into the specifics. But for example, Tito, bellow seals, and Boston, those three are the bolded, and then the non-bolded is the skeleton or the curious sentence. So altogether, Tito also provided information on bellow seals research and development activities in Boston. So we've taken an ordinary paragraph, salted it in randomly to add in a nuclear relevant sentence. And we repeat this process randomly for all 20,000 plus documents. So in the end, we have, what do we have here? We have our meat, a bunch of slices of meat, each one being a paragraph or so. If it was 20,000, it'd be up to the roof, but this is just what we have here. And you notice that some of our paragraphs are not salted. That's intentional because we have very fine taste. We don't subsist on just salt. We also want some pepper. What's pepper? Again, let me see if this will work. Nope. Okay, we'll just use our imagination again. Pepper is just like the carrier sentences, but we call them useless sentences. So we're going to insert a nuclear item in that sentence, but the sentence is going to be something irrelevant, nothing really substantial. So it would be, for example, bellow seals is more expensive than previously understood, right? A random sentence that, although it makes sense, it doesn't add any additional knowledge about where something is produced or who is producing it, something to throw the model off. So let's grab another plate. Let's take the meat that we have not salted and add pepper into that. So altogether, here's what our data set looks like. Some of our paragraphs are going to be salted. Some of them are going to be peppered with useless information. And then some are not going to be touched at all. At most, we'll have maybe a little bit north of 300 paragraphs that are salted or peppered, salted and peppered. But most of the knowledge is going to be as is. So this is going to be a very tedious task for the model. Now, let's come back to reality. What just happened? I apologize if I made you hungry. That was not the intention. But let's illustrate this very complicated process more intuitively. When creating our data set, it's a three-pronged approach. First, we have our salting protocol. This is one part, the carrier sentences, the sodium in our equation, just a skeleton of sentences, nuclear relevant that we can insert nouns, and the one part carriers. So specific who's, like named people, where's, locations such as cities, and then the element Y, or like capital Y. That's going to be our specific nuclear item. So if it's a silly item, it's going to be a pixie dust. If it's nuclear gas centrifuge, it's going to be bellow seal. So very specific items. Now we salt the squad corpus. That's the next step. That is, we split the squad data set into sections of sentences, and then in between the sentences, we add in our salt. So it makes it look like it's part of the actual paragraph. And then finally, we add some pepper for robustness, applying meaningless sentences to whatever is unsalted. Now that's our data set. How do we train or refine this off-the-shelf BERT model? So training a language model, especially BERT, is no different than any other mass language modeling training in this case. So we simply take a sentence, right? And here I've better an example. The quick brown fox jumps over the lazy dog. Here we're going to put a mask over a fox. So now it's the quick brown blank jumps over the lazy dog. In this case, we're asking the model, hey model, consider what comes before this mask, the quick brown, and what comes after this mask, jumps over the lazy dog, hence the term bi-directional encoders, and try to predict as best as you can what goes in that blank. And if it's correct, it will predict fox, and you'll get it correctly. So in this sense, this training is actually a self-supervised method, which is really quite straightforward. It usually takes us a day just to refine it, and we get some pretty good results. And so during this training, we need to consider just two main questions, right? It's a battle between an off-the-shelf pre-trained BERT in blue, right? Something that we just take, general wiki knowledge versus our fine-tuned BERT that's been trained additionally with our corpus, right? The thing that we feed it, the meat with the salt and the pepper. Will this fine-tuned BERT provide better insights into questions that a nuclear analyst will have? That's the question to consider. That's what we're going to try to understand in our results. And speaking of results, so we've talked about our experimental setup. We have our training set. We have our models. We know what kind of criteria we're going to use. Now let's go ahead and interpret that. In this instance, I'll hand it off to my colleague, Megan.
Sure. Thanks, Alejandro. So far we saw some details as to how we're going to salt and pepper our database in order to induce nuclear domain specific knowledge in our corpus. In the next part of the presentation, we're going to be looking at some of the performance metrics. We're going to be looking at some of the strategies that we've developed in order to evaluate our question answering system. And later on, we're also going to be looking at some of the auditability approaches. Okay, so let's start by looking at the evaluation framework that we've developed. So we've essentially developed a set of closed style questions, as Alejandro also mentioned. And these closed style questions are nothing but fill in the blank kind of questions that are used to extract information from the language models. And for our experiments, we are essentially interested in two broad categories of questions. One is the where kind of questions, which are used to probe the language models for information about a location. And the second category is the who kind of questions, which are used to probe the language model about information about a specific person. So let's look at some examples of the probe questions, right? So hydrogen sulfide could be an item of interest to a nuclear analyst. And a nuclear analyst can ask, okay, hydrogen sulfide is manufactured at dash, right? Where you expect the model to output the name of a city or a place or a location. Another item of interest to a nuclear analyst could be a bellows seal. And a typical who question could be, bellows seal is developed by dash, where you expect the model to output the name of a person. And so throughout the results and the performance graphs that I'll be showing you for our question answering system, the model input are these closed style questions, and the model outputs are the tokens and the associated probabilities, which according to the model are the best choice for filling up those blanks. Okay, so now let's look at some examples of the probe questions and the answers given by the pre-trained and the fine-tuned models, right? So bellows seal is fabricated at dash is an example of a probe question. And so if you ask this question to the pre-trained off-the-shelf BERT model, this is the top answer, right? And if you ask the same question to one of our fine-tuned models, the top answer is actually Boston. And this seems slightly more relevant to the question that we are asking. And it so happens that the correct answer is also Boston. Let's now look at some other examples. So hydrogen sulfide is produced at dash. The answer given by the pre-trained model is pH. Not very sure why the pre-trained model thinks pH is a good answer. Maybe because pH is related to chemistry and our question is about hydrogen and sulfide. So maybe that's the reason. But if you look at the answer provided by the fine-tuned model, it actually says Detroit, which also happens to be the correct answer. So I'm going to list a few more examples here by which you can see that in all these examples, we see that the fine-tuned models don't just give the the correct answer, but they also associate these answers with a high probability. All this goes to show that the fine-tuned models have a higher confidence in the answers that they think are best suited for those blanks. So the point that I'm really trying to drive home is that when you're working with language models for a domain-specific application, the fine-tuned models are definitely a better candidate than the off-the-shelf pre-trained models. Okay, so now with that in mind, let's now look at some of the performance metrics and some of the graphs that will help us better understand our question answering system. So we're going to be looking at some graphs which will mainly help us understand three main aspects, right? So the first aspect is to understand what is the influence of the different probing strategies on the question answering model performance. We will also be looking at some graphs that will help us understand what the effect of different sorting methodologies is on the recallability of the question answering system. And finally, we'll also be looking at how does the model behave when you do both salting as well as peppering. Okay, so now let's look at what is the influence of the different probing strategies. So in this graph, this graph shows the question answering model performance. So on the y-axis is the top 10 recall, and on the x-axis are the different fine-tuning epochs. So just as a reminder, our starting point is a pre-trained BERT model, and we fine-tune this BERT model on our nuclear domain-specific corpus, right? And for this graph, we have just probed the fine-tuned models and looked at the response. And you see from this graph that after 75 epochs or so, our top 10 recall sort of settles at about 0.6, 0.7. So this is one thing that you can definitely do, that you can definitely probe only the fine-tuned models. But you can also go a step further, right? And you can leverage both the fine-tuned and the pre-trained models. In that, you can compute the difference between the fine-tuned and the pre-trained models. And the orange line in the graph shows the response that we got when we did that. And from all of our experiments and our analysis, we've consistently seen that when you do this differencing between the fine-tuned and the pre-trained models, you do see some improvement in the recallability of the language models. Okay, we went one step further, and we adopted a strategy what we like to call probing and rolling up. So when it comes to a nuclear analyst, he can have several ways of asking the same question. So a nuclear analyst can ask who has bellow seals, or he can ask who possesses bellow seals, or who manufactures bellow seals, and so on and so forth. So what we can do is that we can feed our models these same set of questions, and we can sum up the responses across these questions, or we can roll up the responses across these questions. And that is a strategy that we call probing and rolling up. And from our experiments, it seems like this rolling up strategy does give like a boost to the performance of the question answering system. And this is something that's also quite relevant for a nuclear analyst, because he definitely has different ways of asking the same question. Okay, so the final probing strategy, which gave us like the best result, is basically the combination of all the three previous strategies. So this involves probing the fine-tuned models, rolling the responses across these questions, as well as differentiating the responses with the pre-trained models. So again, with all these graphs, the main point that I want to highlight is that when you're working with language models for the task of question answering, the way you probe the language models for information can have a great impact on the recallability, right? So the probing strategy can be really influential in your final results. Okay, so now let's look at what is the effect of different sorting methodologies on the overall performance. Right, just as a reminder, by sorting, this is a slide that Alejandro also presented. So this is an example of a paragraph from Squad database. This paragraph talks about Tito. So we refer to such paragraphs as who paragraphs because they are referring to a person, right? And with our sorting process, we are essentially introducing a sentence in this paragraph that connects Tito with a nuclear item of interest. So this is our sorting process. And now let's look at some graphs. So the graph on the left shows the question answering model performance when we solved the who paragraphs. So like a paragraph that I showed you just now, a paragraph about Tito. And on the right is the question answering model performance when we solved the where paragraphs. And what we interestingly saw through our experiments is that when we solved the who paragraphs, the performance on the where questions is more accurate. And when we solved the where paragraphs, the performance on the who questions is more accurate. So this was a really interesting observation that we had. And so we understand that the way these language models learn different things, the way these language models form semantic associations between the different tokens can be really influenced by how and where you solved the information in the training corpus. Okay, so now let's look at what is the effect of peppering our corpus. So just again, as a reminder, the pepper sentences are the distractor sentences. And we essentially do this step of peppering because we are interested in seeing how much is the model's performance being affected or being degraded because of the presence of these pepper sentences, right? We really want to see if the model is robust enough to the presence of irrelevant information in the corpus. Okay, so on the left again is the question answering model performance when we solve the where paragraphs, but here we do just the salting. And on the right is the model performance when we do both salting and peppering the where paragraphs. And in order to have a fair comparison, I'm only showing those graphs where we are salting or peppering just the where paragraphs. So the two things to note here. So the first thing is that because we are salting the where paragraphs, we kind of expect the performance on who questions to be better. And that's what we see in both these plots. And the second thing to note is that the overall trend seems to be that even when you do this peppering process, even when you introduce these distractor sentences in the corpus, the model performance does not seem to degrade, right? So it's actually quite encouraging to know that these models are robust to the presence of even distractor irrelevant information in the corpus. And that information is something that could be very helpful to a nuclear analyst. Okay, so now that we've looked at some of the results, let's talk about auditability. So what do I even mean by auditability and why is it even relevant to anybody? The thing is, most machine learning and deep learning models these days are infamously referred to as black boxes. So you feed certain inputs to these models and you get back certain outputs, but usually there is no evidence as to why the model came up with a particular answer. And as far as nuclear analysts are concerned, they are not just interested in getting the best answer, but they are also looking for those supporting documents that contain evidence on the basis of which the model came up with a particular answer, right? So that is why auditability is important for a nuclear analyst. And so our approach to auditability is to point to the exact source paragraph that contains evidence for the answer provided by the language model. And for now, we have quite a simple algorithm for auditability, and I'm going to briefly walk through that algorithm. So as a first step, you have the question and you have an answer. You concatenate the question and answer string in order to form this concatenated string. As a next step, you compute the embeddings of this concatenated question plus answer string. Embeddings are nothing but a mathematical way of representing your text. And those of us who have some experience working in the language processing field know that there are several ways of obtaining word and sentence level embeddings. So in this step, we compute the embeddings of just the question and answer string. Then we do the same thing for all of the different paragraphs in the corpus. And then we finally do a similarity search wherein we're trying to find the paragraph that's closest to our question plus answer string. We're basically doing like, which is the paragraph that's most similar to my question and answer in this high dimensional embedding space. Okay, just as a side note, I do want to mention that this approach of finding few paragraphs among, so many paragraphs in the squad database. So as Alejandro mentioned, we have about, I think, slightly more than 20,000 paragraphs in the squad database. And what we want to do is to really find those few paragraphs that contain evidence for the answer. So we like to refer to this problem as, a typical needle in a haystack problem where, there are just so many paragraphs and you're just looking for few of them that provide valid evidence. Okay, so these are some quantitative metrics for our auditability results. So these are the, what I've shown here are the top 10 recall values for the where and the who kind of questions. And usually for an analyst, it's probably not that time consuming to go through 10 documents. It's certainly easy to go through 10 documents as opposed to going through 20,000 documents looking for an evidence for the answer. And so we think this approach could also be very interesting for a nuclear analyst and could definitely cut down their burden when they want to, find more justification for the answer given by the model. Okay. After looking at these quantitative metrics, I also wanted to show you some examples of the paragraphs that are being returned by our auditability algorithm, because numbers only tell so much, right? So this is an example where the question is who produces bellows seal. The answer is Tito. And this is the top paragraph that's returned by our auditability algorithm. So you see this paragraph talks about Tito, which is good. What we have also highlighted here is that this paragraph actually contains the sentence that relates Tito and bellows seal. So this was the exact salt sentence that we had inserted in the corpus during the salting stage. And it's quite encouraging to know that our auditability algorithm is actually able to point to exact this paragraph that contains evidence for the answer. Some more examples. So if the question is, now we're looking at a where kind of question. So where is bellows seal produced? And this is again the top paragraph that's returned by the algorithm, right? So paragraph is about Boston. And you see again here, the highlighted sentence is the salt sentence that relates Tito and bellows seal in Boston. And so this is exactly the paragraph based on which the model can say that when you ask where is bellows seal produced, the answer should be Boston. Okay, so just for the sake of completeness, I also wanted to show you some examples where the current auditability algorithm might fail. So here is an example. So where is hydrogen sulfide found? The correct answer is actually Detroit. And this is the top paragraph that's returned from the auditability algorithm. So this paragraph, you see, we have highlighted in blue. This paragraph does mention hydrogen, right? But this isn't exactly the paragraph that we're looking for. We are looking for a paragraph that connects hydrogen sulfide and Detroit. But it's possible because of the similarity search algorithm that we are doing, because this paragraph has so many mentions of hydrogen, the search algorithm thinks that this is probably the best paragraph that's closest to the question that we are asking. So just for the sake of completeness, I also wanted to show you some of the challenging examples that we have, wherein the top paragraph returned by the auditability algorithm might not be the most relevant. Okay, having looked at the auditability, now I'll pass it on to Alejandro, who will walk us through some of the ideas that we have to extend the current work in the future. And he will also have some concluding remarks for us. So over to you, Alejandro.
Thanks, Mega. So as we've seen from the results and the auditability, it's actually quite promising the work that we have, that our fine-tuned model is actually doing something worthwhile. And this is something that we really want to catch on to. Like, let's see, okay, can we make this any better? The answer is always, of course, yes, an optimistic yes. Specifically, there are 3 solutions that we're looking at the moment to really make this move forward. So starting with our first approach here, I talk about how BERT off the shelf is preaching from a selected few Wikipedia articles. As you might imagine, of this set that's been pre-trained on, it may come across words it's never seen before, especially in the nuclear domain setting, right? How does BERT interpret bellows seal if it's never seen it before? How does it encode that? Our fear, though, is that for these specific types of nuclear vocabulary, these nouns, it may split apart the token just as a natural remedy for a word that doesn't fully understand. And this is going to be, of course, suboptimal. So one way to do this is to enhance the BERT vocabulary, right? Take BERT, take it to school, and have it learn nuclear terminology. How do we do this in a model? This one paper called The Expert actually outlines a use case within the biomedical sphere. Now, it is in biomedical, but the crossover from biomedical to nuclear non-proliferation should be seamless. And the way it works is fairly simple. Uses both a combination of an extension embedding layer with the extension module to represent a vector representation of a word it's never seen before. So this is quite revolutionary and has very good hopes for our future. Being able to teach our fine-tuned model, words it's never seen before, a vector representation. So that's the first one. Our second one is actually a team up with another project in parallel with ours called NuCalum. NuCalum was a different side project that was also developed at PNNL. And what's amazing about NuCalum is that initially it's been trained as a classification model. So not necessarily mass language modeling, but we have documents. Let's first predict a binary outcome. Is it nuclear related or is it non-nuclear related? And then additionally, multi-class classification. So if it is nuclear related, what type of nuclear document is this about? Now, of course, we're doing mass language modeling, but how this applies, right, is that NuCalum has been pre-trained from scratch on nuclear domain data. In our instance, we use something off the shelf that's already been pre-trained on Wikipedia data and simply fine-tune it. So the great thing about pre-training is if you have time and if you have money and lots of money to train a BERT model from scratch, pre-train one, then you can do it. And so our hopes is if we can re-engineer this, reverse engineer NuCalum, use the weights it's learned and apply it to our model. So we not only have the fine-tuning stage, we have fine-tuning and pre-training, right? We can only imagine the result we can get. As you can see from the table on the right-hand side, it's doing well, quite excellent in distinguishing between at least classifying nuclear documents from non-nuclear documents. So we have very high hopes for this one as well. Finally, a personal favorite of mine, I think is going to be very exciting, is multi-hop reasoning. The idea that if A, then B, therefore C, right? So the way we've been probing these questions is that we ask a very flat out question. That's the only context it gets. Like where is bellows seals produced? Or maybe we want to more ask who is producing bellows seals? And that's a bit more ambiguous. So before we dive into that, let's look at this paper that focuses on multi-hop reasoning. So in this case, we have one clause, static electricity causes sparks, and a different clause, sparks can cause a forest fire. So then it infers, okay, let's connect the dots here. Static electricity can cause a forest fire. Now, we're not in the business of doing forest fires or even having a static electricity here, but how can we apply this to nuclear domain questions? So in this context, what if we ask the question, who is involved in uranium enrichment? And the answer should be Tito. So the way this would represent, right? If we have a trained corpus where we have a sentence, Tito has bellows seals. Normally we think, okay, so what? He likes to collect some bellows seals for his own entertainment. But if we add an additional separate independent clause, bellows seals is used in uranium enrichment, all of a sudden we could connect the dots. If A and B, therefore C, Tito is involved in uranium enrichment. If we can solve this aspect, this will drastically open up our doors as to what the model is capable for and the type of insights it can produce for nuclear analysts. Now, there's a very exciting future. With that being said, this does end this presentation. I thank you all for your time and attention, and we'd like to open up for any questions you may have. Thank you.
Super, thank you very much. I see we have a couple questions that we can get started with, but before we go there, I'm gonna take the privilege as host to ask my question. So we're working with creating a chemical domain sort of specific model, and we've been working with Svetlana Volkova at PNNL for that. And it seems to me that as we go to each new domain or each new subdomain, we kind of have to do this all over again. And my sort of thinking on this is that there, as you mentioned, there are a number of models that are around biochemical languages, but those don't work at all for straight chemistry, where you're asking questions about synthesis of molecules and stuff like that. So is our lot in life for every one of these new domains that we want to go, whether it's nuclear non-proliferation or chemistry or biochemistry or medicinal chemistry, like, do we have, or is this going to be a thing where we have to go and retrain or re-augment, transfer these models to every new domain?
So sure, I can take that question, Dave. So that is true. As of now, it seems like for every new domain, that's what people are doing. So for a nuclear domain, they're training nuclear specific model, and for biomedical domains, and so on and so forth. But I know that there have been some efforts where people are trying to do multimodal models, or people are trying to do multitasking models. So why not think about a model that can be a multi-domain model, so to speak. So yeah, I would think that that's definitely possible. Of course, it's going to take time, money. Yeah, so that's what I would think. That would be my first thought.
So just quick follow-up then. In your thinking, is the time and money, is that needing to go into new methods, or is that needing to go into training? Just basically throwing iron at the problem and training bigger and more complex models.
I think it's going to be a combination of both.
Okay.
Yeah.
Right.
Thank you.
The way Megan mentioned, we'll need the compute power, right, to get more insights. So we don't know, for example, what the current state. We could theorize, but unless we put it into practice and see what the actual results going to spit out, right, that's where the computational part comes in. So it is a kind of mix between the two.
Got it. So I have two questions here for you right now. The first one kind of relates to this last point that you made. Would the recall still be high if you probe the fine-tuned model with a question that is not available from the corpus that the model is trained upon?
So will the recall still be high if the model is trained with the question? So the questions that we use, the model is not aware of the question itself. The model is just aware of these solving sentences. And so you can come up with any question as long as you're asking the same, item of interest. As long as so you can ask a question, you can ask any question about bellows seal, but the model needs to know about bellows seal. But what question you ask, it's up to you.
Great. Okay. Thank you. By the way, for those who don't know, a bellows seal is a mechanical seal that has a spring replaced with a bellows. So it's a very chemical engineering thing to know that. Okay, how much salting do you do compared to peppering? And the question is 50-50, 70-30.
Yeah, so,
I think Alejandro, yeah, go ahead.
Yeah, so the most for each of them would be equal 50-50, but we also have to remember that of the salting and of the peppering, it's still a somewhat small percentage of the overall context. So we have 20,000 plus documents, and we have 5 different categories as well for each of them. We can have at most 320. So 160 for salt, 160 salted paragraphs, 160 peppered paragraphs. So at most 320 is what we're looking at.
Super, thank you. We have one more question. Great talk. How do you envision transformers to enhance these methods?
So for the question answering, we are inherently using a transformer-based model. So we are using a BERT model. We have some thoughts of integrating auditability also within by using transformers. So we have some first thoughts as to training a transformer-based model that will spit out not just the answer, but it will also spit out the document ID that might be helpful for auditability. So yeah, these are just thoughts, first thoughts, and we're still working on refining those. But that's how I would envision using transformer-based models for auditability as well.
Super, thank you very much. We have time for any additional questions. If folks want to use the Q&A button in the bottom of your screen to type in your question for the Alejandro and Mega. All right. Well, it looks like we've answered all the questions and come to the end of our time today. I want to thank you again on behalf of all the participants and the eScience Institute and the University of Washington. So thank you very much for coming today. It's been a really wonderful presentation, and thank you for your time.
Thank you so much. We're thrilled to be a part of this seminar series. So thanks again.